In today's rapidly evolving digital landscape, the sheer volume of data and the complexity of computational tasks have surged to unprecedented levels. Traditional computing systems, once stalwart workhorses, often find themselves inadequate to meet the demands of modern applications. Enter distributed computing, a paradigm that wields the collective might of numerous interconnected computers to efficiently solve complex problems. In this in-depth guide, we will delve into the intricacies of distributed computing, exploring its foundational principles, the multitude of benefits it offers, the formidable challenges it presents, and its myriad real-world applications. Additionally, we will investigate the diverse types of distributed computing systems that have emerged to address specific use cases. Before we begin, consider subscribing to the channel for more content. You can also share your thoughts in the comments section. Understanding distributed computing. Distributed computing is a paradigm where multiple interconnected computers collaborate on a single task or a set of tasks. These computers, referred to as nodes or processing units, are dispersed across a network. They communicate with one another to coordinate and execute tasks concurrently. The primary goal of distributed computing systems is to decompose a problem into smaller subproblems, allocate these subproblems to individual nodes, execute them in parallel, and subsequently aggregate the results to derive the final solution. Key components of distributed computing. 1. Nodes. Nodes represent individual computers or servers within the distributed computing system. These nodes can possess varying degrees of processing power, memory, and storage capacity. 2. Network. A robust and high-speed network infrastructure is paramount for facilitating communication and data exchange between nodes. This network can span a local environment, e.g., within a data center, or extend globally, e.g., across the Internet. 3. Middleware. Middleware comprises the software components that facilitate communication and coordination among nodes. This includes message passing systems, data serialization tools, and distributed file systems. 4. Task scheduler. The task scheduler plays a pivotal role in the distributed system by assigning tasks to individual nodes, overseeing their execution, and monitoring progress. It ensures equitable task distribution for optimal resource utilization. Benefits of distributed computing. Distributed computing offers a plethora of advantages that make it an appealing choice for a wide array of applications. 1. Parallel processing. Distributed systems excel at parallel processing, drastically reducing the time required to complete complex computations by dividing tasks among multiple nodes. 2. Scalability. The horizontal scalability of distributed systems, achieved by adding more nodes, offers a cost-effective approach for handling escalating workloads without compromising performance. 3. Fault tolerance. Distributed systems inherently possess fault tolerance mechanisms. In the event of node failure, the system can seamlessly continue processing on available nodes, ensuring uninterrupted operations. 4. Resource utilization. Distributed computing optimizes resource usage by efficiently distributing tasks, minimizing idle time on individual nodes and enhancing overall system performance. 5. Geographical distribution. Distributed systems accommodate geographically dispersed nodes, enabling global collaboration and data processing, which is especially beneficial for multinational organizations. Challenges in distributed computing. Despite its numerous merits, distributed computing also presents a series of formidable challenges. 1. Complexity. Designing and managing distributed systems can be exceptionally intricate due to the need for synchronization, fault tolerance mechanisms, and data consistency across nodes. 2. Communication overhead. The exchange of data between nodes can introduce communication overhead, potentially impacting system performance and efficiency. 3. Security. Distributed systems are susceptible to a range of security threats, including data breaches and distributed denial of service (DDoS) attacks, necessitating robust security measures. 4. Scalability challenges. Effectively scaling a distributed system while maintaining performance can be a delicate balancing act. Improper scaling can lead to resource inefficiencies and hinder system stability. Types of distributed computing. Distributed computing encompasses several distinct types, each tailored to specific use cases and requirements. 1. Cluster computing. Cluster computing involves connecting multiple computers or servers, often referred to as nodes, into a single system. These nodes work together to solve complex computational problems. Cluster computing is commonly used in scientific research, simulations, and high-performance computing (HPC) applications. Clusters are designed for high computational performance. They excel in tasks requiring massive parallel processing, such as weather modeling, protein folding simulations, and financial modeling. Nodes in a cluster share resources like memory and storage, but they often have dedicated processors. Communication between nodes is usually high speed, reducing latency. Examples: Beowulf clusters, used in scientific research. Hadoop clusters for big data processing. 2. Grid computing. Grid computing extends the concept of distributed computing by pooling computing resources from disparate locations and organizations. It aims to solve large-scale problems that require significant computational power and storage. Grid computing is commonly used in scientific and academic research. Grids link together resources such as computers, data storage, and specialized hardware from different administrative domains. Users can access resources across the grid as needed. Grids often facilitate the formation of virtual organizations, where participants collaborate and share resources for specific projects or research initiatives. The Open Science Grid, OSG, for scientific research. European Grid Infrastructure, EGI, for various applications. 3. Cloud computing. Cloud computing delivers computing resources, including processing power, storage, and software services, over the Internet. It has revolutionized how businesses and individuals access and utilize computing resources. Cloud computing is categorized into 3 service models: Infrastructure as a Service, IaaS, Platform as a Service, PaaS, and Software as a Service, SaaS, each offering different levels of control and abstraction. Clouds can be public, private, or hybrid, depending on whether they are available to the general public, restricted to a specific organization, or a combination of both. Clouds are designed for scalability, allowing users to easily scale resources up or down based on demand, ensuring cost efficiency. Amazon Web Services, AWS, Microsoft Azure, Google Cloud Platform, GCP. 4. Edge computing. Edge computing brings computational resources closer to the data source or edge of the network, reducing latency and enabling real-time processing. It is particularly valuable for applications that require immediate responses and low-latency interactions. Edge computing minimizes the time it takes for data to travel from the source to the processing point, which is critical for applications like autonomous vehicles and industrial automation. Computation is performed on devices or servers at or near the edge of the network, reducing the need for centralized data processing. Examples: autonomous vehicles processing sensor data at the edge. Industrial Internet of Things, IoT, applications. 5. Fog computing. Fog computing extends edge computing by adding more processing capabilities and intelligence to edge devices. It enables localized decision-making and analytics, reducing the need to send data to centralized cloud servers. Fog computing devices can analyze and act on data locally, enhancing responsiveness and reducing bandwidth usage. Fog computing architectures can be scaled by adding more fog nodes as needed, providing flexibility in managing workloads. Examples: Cisco's Open Fog Consortium promotes fog computing. Smart cities with fog nodes for traffic management. 6. Peer-to-peer, P2P, computing. Peer-to-peer computing is characterized by a network of interconnected computers or peers that share resources and data directly with one another without relying on a centralized server. P2P networks are often used for file sharing and content distribution. P2P networks have no central authority or single point of failure, making them robust and resistant to censorship. Peers in a P2P network can share files, processing power, or even internet connections. Examples: BitTorrent for file sharing, blockchain networks for decentralized ledger technology. These various types of distributed computing cater to specific use cases and requirements, offering diverse solutions for addressing the ever-expanding computing needs of today's digital world. Understanding these types allows organizations and individuals to choose the most suitable approach for their specific applications and workloads. Real-world applications of distributed computing. Distributed computing finds extensive application in diverse fields and industries, underscoring its pivotal role in contemporary technology. 1. Big data analytics. Distributed systems such as Apache Hadoop and Apache Spark power the processing and analysis of massive datasets, enabling data-driven insights at scale. 2. Scientific research. Distributed computing is indispensable for scientific simulations, weather modeling, and molecular simulations, allowing scientists to explore complex phenomena. 3. Cloud computing. Both public and private cloud infrastructures leverage distributed computing to deliver on-demand services and resources to businesses and individuals alike. 4. Content delivery networks, CDNs. CDNs, through their distributed server networks, ensure the rapid and reliable delivery of web content to users across the globe, enhancing user experience. 5. Blockchain. Distributed ledger technology relies on a network of distributed nodes to maintain a secure and decentralized record of transactions, underpinning the cryptocurrency and digital asset ecosystem. Distributed computing stands as a cornerstone of contemporary computing, offering the means to address intricate problems efficiently, process vast troves of data, and provide scalable, fault-tolerant services. In an era of relentless technological advancement, distributed computing assumes an increasingly central role in shaping the future of computing and fostering innovation across a multitude of domains. A thorough grasp of its principles, the various types it encompasses, and its potential is essential for those looking to harness its boundless power and remain at the vanguard of technological progress. Remember to check the channel page for more insightful content.